is showing 12:10, so we're going to go ahead and get started. Thank you again for your patience. So sorry about that. Looks like our links just got switched, but we really appreciate you all being flexible and still joining us here today. So of course, this is our August forum. And if you're not familiar with Partners, we are a nonprofit organization based out of Scott County, Iowa. And our whole goal is to improve the health and stewardship of our watersheds. And one of the ways that we do this is through our educational forum. So today we're going to talk about agricultural best management practices. And before we do that, I just wanted to touch a couple things. So we've got some Zoom housekeeping here really quick. This presentation is being recorded and will be uploaded to the Partners of Scott County Watersheds YouTube page within about a week or so. So if you want to reference something or if you just forgot, you can go back and find that. If you have any questions throughout the presentation, please enter those into the Q&A box at the bottom of your screen, and then we'll answer those at the end of the presentation. If you have any issues with technical difficulties, maybe you can't see the slide or your audio went out, whatever it may be, please use the chat function and change the recipient to ATEC, our forum moderator. We do have some additional upcoming events, so do keep these in mind. We have a trash cleanup in a stream coming up next month. And then what's in October, but I'm sure we'll be here before we know it, is our fall snapshot. So that's our volunteer water quality monitoring day. We need about 35 volunteers for that day. So if you're available and interested, do consider joining that. And all of this is available on extremecleanup.org. And of course, we couldn't do any of these things without our partners. So we are incredibly appreciative of all the people that support us, both through an organizational standpoint and maybe sharing resources to our financial partners. So thank you to everyone who's helping us help our watersheds. You can be a part of those people too. So we have some different options for ways to get involved, and all of this is available on our website. And with that, I think I'm going to go ahead and turn it over to Brian here, the star of our show. So I'm going to stop sharing my screen and switch it over.
Okay, how are we looking on your end?
It's looking great.
Perfect. All right, I appreciate the opportunity to be here today. My name's Brian Dougherty. I'm a field extension agricultural engineer with Iowa State University. And basically today we're going to talk about some BMPs for improving water quality and soil health. So let's get into it here. Basically what I want to do is just kind of start out with some background, why we have water quality issues in Iowa that we see. Then we'll just kind of skim through the Iowa nutrient reduction strategy. I'm sure most people are probably familiar with that and have seen it before. Talk about some of the infield and edge of field practices that you can use for improving water quality. But then really what I want to get into is this connection between water quality and soil health, and how can soil health help us improve water quality. So just to start off with here, if we're thinking about water quality, basically we've got two different issues. We've got surface runoff and we've got subsurface drainage. Those are our two main sources of water. They're going to go into our rivers and lakes and streams. So for surface runoff, I kind of view that as probably, the worst of the two. If I had to pick one, I'd rather have more drainage and less surface runoff, because that surface runoff is going to carry sediment with it and anything that's attached to that soil particle. So all of your nutrients, possibly some pesticides, if they're still attached to that soil particle, all of that can go with it and into your waterway. Subsurface drainage is a different challenge. So there's still possibility of losing nutrients there, but they're going to be our soluble nutrients. So mostly nitrate, nitrogen is what we're concerned about here. And there is a small amount of dissolved phosphorus in that as well that can cause some water quality issues if it gets into a water body that is phosphorus limited. So if we think about surface runoff first, if you think about the soil as a sponge, that's kind of a good way to think about, what leads to surface runoff happening. So basically, There's two things that could happen to that sponge that would prevent it from taking in water. One, is there some sort of barrier or crust on the surface of that sponge that's preventing water from infiltrating? And the second is that that sponge is just completely saturated and it just physically can't hold any more water. So for a given condition of that sponge, as you add water and increase the rate at which you're adding that water, in other words, a heavier rainfall, you're going to get more runoff, you're going to get more soil erosion if that surface isn't protected, and more sediment delivery to our streams. So I really like this image on the left here where they've got a close-up view of a water droplet hitting the surface. That might seem like a very minor impact to us, but if you're a soil particle or you're a little microbe in the soil, that's like a bomb going off on the surface of the soil there. So we have to keep in mind that those raindrops do have a tremendous amount of force when they hit that surface. So protecting that surface from that direct raindrop impact is very important. Just thinking about erosion, this is showing wind erosion here, obviously, but we have both in Iowa. It's important to remember we're mostly concerned about water erosion, but this just happened this year in Western Iowa, this dust storm that came out of, Western US. But if you do some calculations and think about what is that actually costing us, if you lose an inch of topsoil, there's somewhere between, depending on how you do the math, $1,500 to $3,000 just worth of nutrients in that soil if you had to buy all of that back and replace that topsoil that you lost. So, as farmers, we kind of gripe about, $10,000, $15,000 an acre land. Well, if you think about what that land's actually worth, the nutrient value in that's not an unreasonable price. So normally I do this a little more interactive. We're on Zoom here today, but I like to ask people what's different between these two pictures. So you've got 2022 on the left, you've got a Dust Bowl picture from the 1930s on the right there. So just think about it on your own there. What do you think looks different between these two? Now this is a little bit of a not great comparison because the colors are a little bit different in these photos, but basically it is color. We've lost organic matter in our soils. The reports are where we had good imagery that soil in the 30s is actually much darker because it had more organic matter in it than what we see today. So shifting to infiltration, so we've got surface runoff. If we want to prevent that, we need to get the water to infiltrate. What is that? Just entry of water into the soil. And that's influenced by a whole bunch of different things: physical characteristics, the structure, the texture of that soil, moisture, cover, how it's managed, all of that goes into infiltration. But if we look at the effect of land use on infiltration, so this is an older study now, back in 2002, but basically they compared a forested environment versus more of a grass environment versus row crops that we tend to have here in Iowa. So this is looking at cumulative infiltration, and you can see as you shift, from what we would consider to be a native type habitat with trees and grasses to more of a row crop systems that we have today, that infiltration rate tends to go down. And a lot of that's due to management. Some of it's probably a little bit unavoidable, just depending on what it is that you're growing. And even the pasture on the right there, this is apparently a pretty poorly managed pasture. Normally we would like to see a better infiltration rate than that in our pastures. So what's happened over time in Iowa? There's a bit of a misconception out there among the public. People drive around and they see a lot of corn. So they think, well, part of the reason we have water quality problems is because we're just growing too much darn corn, right? Well, if you look at the data, that actually hasn't changed that much. Back in the 1930s, we had almost 12 million acres of corn in Iowa. So we're actually not growing that much more corn now than we did, even going back almost 100 years. What's changed is we've added soybean acres and we've lost our hay and oats. So if you think about the 1930s, we had a lot of draft animals. This is, pre-World War II, not very many tractors around. So you had to feed those animals. You grew hay, you grew oats, you had a more diverse farm, you had integrated livestock. We've lost a lot of that over time as we've shifted away from that type of farming, more mechanization, more fertilizers and pesticides that allow us to farm differently. And so now we grow different crops, and we've got a much different landscape now than we had historically. So why do we have runoff? Getting to it here. We've got more row crops, as I just showed. We tend to see lower infiltration rates in those row crop acres. And we are seeing more extreme rainfall events over time. The atmosphere seems to be warming a bit, it's holding more moisture. We're getting more of these intense rainfall events. This is just a graph showing flow from the Cedar River and Cedar Rapids. And if you plot that out over 100 years, that trend is increasing. And I'm going to get into this later, but soil health is also a big part of the connection here. So looking at subsurface drainage, there's a lot of controversy around this. So essentially what that's doing is once that sponge is fully saturated, we're just trying to remove some of that excess water, what we call gravitational water that just flows through that soil and isn't being held by gravity. That helps create storage space. If you have another rainfall event that comes along, it does help reduce surface runoff. And again, a lot of debate about this. Does it cause flooding? Does it not? The literature that I've seen on it seems to indicate it's kind of an it depends, but generally it does not increase flooding. It depends on what scale you're looking at in the landscape. What it does do is if you talk about, the hydrologic terms, if you don't have drainage and you get a heavy rainfall event, you get a very steep hydrograph, you get a big peak of runoff, and then it drops off quickly. What drainage does is basically flattens out that curve. So you get a little bit more water into the soil, but then that water is going to come back out a few days later. So it kind of flattens it, but you get more water delivery to the streams after a storm event. And the main issue that we hear a lot about here in Iowa is that we do have higher nitrate concentrations in that subsurface drainage than we're going to have in our surface runoff. So that brings us to the Iowa nutrient reduction strategy. I'm not going to spend a lot of time on this. I'm sure most of you are familiar with it, but basically a task force came out with a plan and said, we need to reduce our loads to the Gulf of Mexico by around 45%. That's our goal. That's what we're trying to get to. So Iowa State did a whole bunch of research on this, looking at all of these different potential things that you could do to reduce nitrate loss and also phosphorus loss. So if you look at things like timing on the top of the chart there, they can make a small impact, kind of infield management type stuff, but the numbers aren't going to get us to that 45%. And it's important to note here, these are not additive. So if you just go down that list and do every one of those things, you're not going to get to that 45%. It doesn't work that way. But if we look at the bigger numbers here, we're looking at things like cover crops and living mulches, essentially keeping that soil covered, over a greater portion of the growing season. That can get us somewhere in the 30 to 40% range as far as reducing the amount of nitrogen we lose in that drainage. So shifting to land use changes, that's where we see very big numbers, but obviously that means you're, either taking that land out of production or converting it to pasture or something like that. And then we've got our edge field practices. Essentially, these are engineering type solutions, so drainage, water management, bioreactors, saturated buffers, things like that. And we see pretty big numbers there as well. So if we want to get to our 40%, we're going to have to do some of these things where we see these bigger numbers. So edge of field practices, there's a whole laundry list of these. I'm not going to go through all of them, but there's lots of different ways to go about this. Buffer strips and things you can do in the field or edge of field, trying to prevent that surface runoff. And then a lot of things you can do to manage that drainage system through controlled drainage and drainage water recycling and some newer practices to keep that water on the landscape or, have less of it leaving out the drainage line. This is just another chart showing essentially the same data, it's just in a different form. I like this because it kind of shows the range on these. So again, the top there, those are kind of our infield practices, changing nitrogen application timing, side dress, and you see there's a lot of variability. Sometimes that actually increases nitrogen loss rather than decreases it. So on average, it's a small net benefit. Cover crops, larger net benefit, but again, a lot of variability because we don't always get good cover crop growth every year. And you get into things again like land use change. That's where we see our big benefits. And then down the bottom here, we've got our edge of field practices, all of the blue bars. Generally, you're gonna see a net benefit with those type of practices. The downside to those is they do tend to be more on the expensive side. So how do they work? Basically, 3 different ways. They reduce sediment delivery. They reduce the concentration of nitrogen or phosphorus in that drainage water. And there's a couple different ways they can do that. You can get more denitrification in a bioreactor, for example. That's basically converting that nitrate back to nitrogen gas, or you're trying to increase plant uptake. The other thing that they can do with the right design is reduce the total amount of flow that's actually coming out the drainage line. Things like, changing your drain spacing, changing the drainage depth. Practices like that can reduce the amount of drainage flow you have coming out of the field. But if we get to our water management goals, just thinking about big picture, what are we trying to accomplish? Basically, we want to do 3 things. We want to increase our infiltration rate, which is going to reduce our surface runoff. So we want to get as much water as possible into that soil. We want to maximize the amount of water that soil can hold, so we don't lose as much of it out the drainage line if we have drainage. And we want to prevent our soluble nutrients from leaving that system. We want to use them up before they get into our water. So that's basically what we're trying to do. And this kind of gets into the second part of my talk here. All of these things, all 3 of those, can be achieved by 1, increasing the organic matter content of our soil, and 2, by building soil aggregates. Essentially, what we're talking about here is improving soil health. So what is soil health? This is the standard NRCS definition: continued capacity of soil to function as a vital living ecosystem that sustains plants, animals, and humans. That's a pretty good definition. Essentially, it's just a soil that can grow a productive crop with a minimal amount of external inputs is kind of the way I think about it. And in order to have a healthy soil, we need to have active biology in that soil, and we need to have a well aggregated soil. So the way this kind of works is that soil organisms, they get carbon or root exudates from plants that feed those organisms in the soil. That carbon is their food source. And then in exchange, they provide nutrients and water to the plant. It's actually that process, that interchange between the plants and the soil biology, that builds soil aggregates. And I'll get into how that works. This is what cycles most of our nutrients in the soil. A good majority that's driven biologically. And that rhizosphere, that area right around the plant roots, that's actually serves as both the digestive system and the immune system for our plants. So we need this to be functioning properly. So what are soil aggregates? If you're not familiar with that term, we're basically talking about soil structure here. They're just clumps of soil particles that are stuck together by organic matter or various glues and carbon compounds in the soil. They can be different shapes. You can see the image on the right there. That's a very well aggregated soil. It's got a lot of different particle sizes there. There's lots of channels for water to infiltrate. It's kind of a cottage cheese look or chocolate cake look is how people describe that. That's kind of the goal. That's where we want to get, is to have our soils look like that, so they can, 1, infiltrate water, and 2, they also have good air exchange. And I'll get into why that's critical as well. So how do we improve aggregation? Kind of getting into how this works. Well, if you think about having more plant growth on the surface, I kind of think of that as kind of the framework, just to protect that soil surface from that raindrop impact, kind of stabilizes the soil, holds it in place. But then we have this process of those plants feeding carbon to the soil biology. And then in turn, that soil biology actually, mostly the bacteria and the fungi is what we're talking about here, they secrete glues and microbe goo. Dead microbe goo is kind of our layman's term for it. They secrete these glues that bind those soil particles together. That's actually how soil aggregates form. The other thing we need to do here is reduce our disturbance as much as possible, mainly talking about tillage there, but there's other forms of disturbance, because that's going to disrupt that whole cycle of aggregate formation, and it's going to break up our macropores and our root channels and our earthworm channels and things like that that help us to infiltrate water more quickly. So just looking at a plant, now this is kind of a goofy schematic here. I don't know why they have a potato growing below ground and a tomato above ground, but anyway, if you ignore that, we're looking at this process of photosynthesis. You probably all remember this from, grade school or junior high science class. Basically, plants they're taking water, they're taking sunlight energy, and they're taking carbon dioxide and they're releasing oxygen. That's where we get the oxygen in the atmosphere that we all live on. So I'm sure we're familiar with that. But the thing we have to remember is the underground part is basically a mirror image of that, only it's doing the opposite thing. The roots actually need oxygen, and the biology around that root system needs oxygen, and it's releasing CO2. So that soil is actually breathing. You can think of it as a lung. So you've got CO2 gassing off the surface of the soil, which can then be reused by the above ground plant. So you can actually see much higher CO2 levels right down in the plant canopy than you would have just in the bulk atmosphere. And that's actually a benefit for crop growth if this system is working properly. But in order for that to work, you have to have a well aggregated soil where that air, it's essentially so it can breathe, kind of like, think about a lung. Your lung tissue has these little pockets in it. The soil works the same way. It has to be able to release that carbon dioxide, you need to be able to take in oxygen for those roots. And it's that process of translocation of sugars or photosynthate or root exudates. You'll hear different terminologies for that. That's an active process. Those plants are pumping that exudate into the soil to feed that biology. And it's pretty incredible what these plants can do. They can actually send signals and feed very specific microbes to make certain nutrients available that they need. So what happens when this breaks down? Well, think about a compacted soil with poor aeration, poor structure. If it doesn't infiltrate water and you can't have that air exchange process working, that means your roots can't breathe, your water cycle breaks down, you start having a bunch of surface runoff, your plants aren't happy, your microbes aren't happy. And essentially, the way I like to think about this is why plants work with that whole underground network, the soil food web, we call it, to build soil aggregates. This is an active process. It's driven by plants and biology. And if we want to have well aggregated soil and prevent our surface runoff, we have to have, a green growing plant, throughout the growing season. I think of it as basically a survival mechanism for these plants. They're trying to create the habitat in which they can thrive. And that habitat is a well aerated, well aggregated soil. So this is basically the take home point that I'm trying to get to here in this presentation. If you look at the big picture, it's dysfunctional air and water and nutrient cycles in the soil that are the fundamental cause of our erosion, our nutrient loss, and our poor water quality. And this is globally. This isn't just a thing that's happening in Iowa. This is happening all over the world. If we look at our environmental issues with soil loss and water quality issues and nutrient loss, they're all driven by the soil that just doesn't function properly. So back, 50 to 70 years ago, we kind of had this old model of soil. We understood that there were chemical and physical and biological things in the soil, but we didn't really put it together and realize what all of those connections were. Just kind of ignored the biology, mostly focused on the chemical side. And, biology, we kind of focused on getting rid of it, essentially. If there were creepy crawlies in the soil, they were generally thought to be bad, and we wanted to get rid of them because they were damaging our crops. Well, we've since come around to realize that that's not really the case. All of these things are important. They all interact. We can't ignore the biology. We have to pay attention to that. So you have to look at the chemical and the physical and the biological, all of the system. But I like to go one step further with that and think of kind of a new regenerative model of how soil actually functions. because soil, if you look at the whole system, it's actually dominated by the biological component. A healthy soil that functions and cycles nutrients and infiltrates water and does all the things that we want it to do, it's a biologically dominated system. The biology, as I kind of went through, actually determines some of the physical characteristics. It's the biology that's building the aggregates. It's the biology that's driving a lot of the chemical reactions that happen in the soil. And it's feeding carbon. The carbon flow through this system is what allows all of that to work, because that's the food source for your microbes. So I like to think about soil this way. So if we just think about, if you wanted to increase your input costs into a farm and reduce resilience, the way I think about it, this is basically how you do it. You start with bare soil, which is going to cost, nutrient loss, erosion, less organic matter. The whole structure, the system breaks down, things don't cycle like they should. And then you have to spend a bunch of money trying to fix it with inputs and tillage and engineering fixes and things like that. But we can flip that whole thing on its head. If you start with a covered soil, diverse plant growth, you reduce all of those environmental losses, less erosion, build organic matter, better structure, your water cycle starts to function, you get more air exchange, and then you don't have to spend as much money trying to essentially fix the problems with that system not functioning properly. So there's two cycles that I think about that are absolutely critical on every farm. The first is the carbon cycle. I'm saying this is more important. The other one's the water cycle. They're probably equally important, but these are 1 and 2. You can order them however, but this is just showing a carbon cycle. This is based on a 200 bushel corn crop here in Iowa. It's actually some data I put together for a class based on the Nashua Research Farm plots. So these numbers are just, general research-based numbers. They weren't actually measured. This is kind of what's found in the literature, but the point here is there's a lot of carbon cycling through this system. You don't really have to pay that much attention to the numbers, but an average soil here in Iowa, depending on how deep you measure and what your organic matter levels are, is going to have somewhere around 100,000 pounds of carbon per acre. So I tend to use the words carbon and organic matter interchangeably. Basically, organic matter is about half carbon by weight. So if we just look at the numbers here and think about what's driving this, what drives CO2 intake, and that's basically plants. It's the biology. The root exudation process I talked about, again, that's the plant doing that, driven by biology. Respiration, this is all biologically driven. That's your plants. You've got your microbes that also respire carbon. I talked about that carbon being released from the soil. Basically, that soil is breathing just like we do. Your residue production, your residue breakdown, that's all a biological process. So if we look at the carbon cycle, and I think this is something that we tend to be lacking in our modern cropping systems, if we think about where's the fertilizer truck in this graph, well, in this case, we're putting on UAN fertilizer. That number is essentially 0. I mean, compared to those other numbers there. So unless you're adding compost or certain types of livestock manure, you're probably not adding much carbon back into the system. We're relying on those plants, that first number there, that CO2 uptake by those plants to drive this system. And if you don't have the soil covered throughout the year, you're missing out on a big chunk of that carbon that you could be cycling through the system. So the whole point here is, again, it's the biology that drives all of these critical soil processes. So water, I'm calling this the second most important, could be the most important. If you don't have water, obviously nothing works. But again, this is just an estimate from Nashua looking at that same 200 bushel corn crop, how much water actually cycles through that system. So ET, that's evapotranspiration. So either off the surface of the soil or, moisture that's released by that growing crop, somewhere around 21 inches a year. Again, that's completely driven by biology. Now, if we look at surface runoff, 3 inches in this case, that's kind of an estimate. That's not measured. We do measure the drainage at this site. But again, what drives that? I talked about the importance of aggregation. It's the biology that builds those aggregates, and it's aggregates and how well drained that soil is that determines how much surface runoff you're going to have. Soil water storage, again, that's how much organic matter you have, what the aggregate structure of that soil is. That's what determines how much water you can store in that soil profile. So again, aggregation is absolutely critical to have a functional water cycle. So a little bit of a trick question here. So I like to quiz the audience on this. What drives precipitation? Most people will say that basically we have absolutely no impact on that. There's nothing we can do about it. And in some areas that can be true. You know, what we call the large water cycle over oceans, there's really not anything we can do about that. But we can have an impact on a large scale on the water cycle over land. And it's actually biology that drives that precipitation process over large areas of land. Because there's been hundreds of research papers on this now, and they found it's actually these little microbes that end up being airborne, plus volatile organic compounds from plants that drive a lot of the small water droplet formation in the atmosphere. And that's important because we need that water droplet formation for regular rainfalls. What happens if you leave that surface bare, you get rid of all of your vegetation, there's nothing for that water vapor to condense around. So there's no nucleus for that water droplet. So the humidity builds higher and higher in the atmosphere. And then it all comes down once as a torrential rainfall. And that's exactly what we've been seeing here over, increasingly over the last several decades. So again, it's critical on a large scale here. And again, if you put cover crops on your farm, you're not going to change the water cycle. But if you do this over a couple million acres, you can actually change precipitation patterns. So if we can get the landscape covered year round, that can help reduce some of these extreme rainfall events that we're seeing. Just an illustration of that, I just took this the other day and I put it on Twitter, but I have this little thermal imaging camera that's kind of fun to play around with, and I was checking soil temperatures in a bean field. And so there's a bare area on the edge. And if you look at that bare soil, it was 72 degrees out when I did this. So beautiful day, not hot at all. It's about 10 o'clock in the morning. That bare soil was already 103 degrees. And it was less than 70 in the shade between the soybean rows. So again, it just illustrates the incredible impact that you can have just by keeping that soil covered with a green growing plant. So why is that important? Well, basically your biology starts to cook when those soils get over 100 degrees, and you actually start killing off your biology. So proteins start to denature at about 105 degrees. And again, this was only at 10 o'clock in the morning. If you came back at 3 in the afternoon, that soil surface might be 120 to 140 degrees. So back to achieving our water management goals. What are we trying to do? We're trying to get more organic matter in the soil, and we're trying to build aggregates. And the way we do that is with what we would call the soil health principles, which I'm sure you've probably all heard about, but I'll just go through them quickly. Mainly here, we're looking at reducing disturbance, keeping that soil covered, and just absolutely critical, keep a living root in that ground year round. So I guess the argument or proposition I'm making here is that we can improve water quality by improving soil health, by following the soil health principles. And there's anywhere from 4 to 10, depending on who you talk to. This is NRCS's list here. Some people have added context to that, which is incredibly important. You have to understand your local context in order to make these principles work on a given property. And we've got a lot of new technology now that can really help us out with that we didn't have 50 years ago. We got much better planting equipment to plant directly into, standing cover crops. We've got a lot of new soil health tests that are coming out. That's still kind of in its infancy. Not going to talk about soil health testing, but there's a lot of things you can do there that you couldn't do 20 years ago or even 10 years ago. And we just generally, there's still so much we don't know, but we do have a better understanding of just the importance of soil biology and nutrient cycling and how that all works together. So just real quickly here, the soil health principles: keep the soil covered, controls your wind and water erosion, reduces evaporation, and all these things that I've been talking about here, and provides a habitat, keeps that soil biology alive, and doing their job, cycling those nutrients for you throughout the year. Minimizing disturbance, tillage is the main disturbance that we talk about, but other things like, pesticide applications can also cause a disturbance to your soil biology. But basically, you drag an implement through the field, you're going to break up those root channels and earthworm tunnels. Hopefully you've got earthworms out there. You're going to break up your aggregates, and just in general, in the long run, you're going to reduce your infiltration rate, and you're actually going to create more compaction. So for decades, we've tried to use tillage to fix compaction and to get water to infiltrate. But once you have an understanding of how that whole system works and what, keeping a green living plant on that surface can do for you, you kind of start to realize that, doing all of that tillage can actually cause more harm than good. And again, the importance of keeping that living root in the ground to feed that biology, build those soil aggregates, and protect the soil surface. If you want to know if you have a healthy plant, if you have a healthy soil, just dig up the roots and take a look at them. You can see that picture on the left. That's what you want your roots to look like. You want to see lots of soil sticking to those roots. You want to see a lot of little fine root hairs. That's an indication that that process is working. As plants are pumping carbon into the soil, the biology is working to build those aggregates, and they should be sticking to those roots. If you pull up your roots and they're bare or naked, we would say, and that's an indication that that process isn't working properly. Diversity is the last one, and I include livestock in that. Some people have that separate. To me, adding livestock, that's just adding more diversity to the system. You can do that with more diverse crop rotations, multi-species cover crop mixes. There's lots of strategies you can use to try to get those established earlier in the season. Again, just keeping that soil covered, providing a living root for the whole growing season. And then we add livestock to the system. That's where I kind of like to think of that. That's the magic. That's when things start to work properly, because there's really no such thing as a truly sustainable agricultural system without livestock. That soil evolved with animal impact, and you take the animals away, now you have to add things back to make up for the fact that you took those animals away. So adding manure can do a lot of good things if it's managed properly. And especially when we look at grazing, basically that just turbocharges this whole process, because they're taking that plant material and they're just immediately breaking it down into a plant available form, whereas that process might take months or years if just left to its own devices. So lots of ways to go about trying to improve water quality via soil health, again, cover crops, grazing, agroforestry, relay cropping, intercropping. I didn't really get into all this stuff, but I just encourage people to experiment. That picture in the bottom right there, that's some 60-inch corn with an early interseed cover crop that we're doing at the Nashua Research Farm. Lots of things we can play around with here, and it's easier if you have livestock in the system. I don't know who I've heard say this, but basically you have the livestock, they can eat your mistakes. So you have that option, whereas if you don't have the livestock, it does make it more difficult and takes a little bit longer. So question I often get, how long is it going to take to improve my soil health, and how long before I see better trafficability in the field and better water infiltration? Classic extension answer, it depends. It depends on how you want to go about this. If you've got a long history of lots of chemical use, you've got a low organic matter soil, you've got a lot of nutrient imbalances, a lot of disease pressure, it's going to take longer. It's going to take time to heal that system. I really like this little graphic on the left here. You can do it good, fast, or cheap, and you can pick any two of those three, but it is impossible to do all three. You can't do it a good job and do it fast and do it cheap. So there's no easy button, I guess, basically the take-home message there, but it is possible. It's just a matter of, individuals deciding how they want to go about trying to do this. So just wrapping up here with some concluding comments. Our loss of continuous living cover, that increased soil disturbance, and limited use of conservation practices over the decades can lead to water quality problems. We are seeing some of that here in Iowa. Some things are actually getting better. Some things are maybe getting a little worse. It's still a continual process of trying to improve that. Healthier soil can definitely lead to cleaner water. And I believe that high production and better soil health can coexist. There are management strategies to implement these things that don't automatically mean you're going to lose yield. We can use those edge of field practices to fill in the gaps where we still have water quality challenges. And I just encourage people to get started on this now. Start small. Don't try to make a change on the entire farm and end up with a disaster. You know, do small scale experiments, maybe take 5% of your land and play around with it a little bit on some of these more innovative techniques. You know, attend field days, webinars, whatever, try to learn from each other, and we can all hopefully improve our soil health over the larger landscape and help address some of our water quality issues here in Iowa. So got some resources here. I'm happy to share these slides or whatever the people, if they want to look at these later, or I can pop them in the chat box. Got another whole laundry list here of different books that I encourage people to read. You know, if you really want to get into this, if you don't have time to read, there's some great podcasts out there that you can listen to in the tractor if you've got some time to kill. You know, the Regenerative Agriculture podcast, Nutrition Farming, the No-Till Farmer podcast has some great episodes, Cover Crop Strategies, all kinds of great podcasts out there. You can get a ton of good information on how to implement some of these practices. There's online trainings if you really want to get into the weeds on some of these things. But I just encourage people to, you know, continue that lifelong process of learning and look into some of these resources. So with that, I will wrap it up. Hopefully we've got time for a few questions if anyone has any.
Awesome job, Brian. I love the picture of you in the corner there again. It's great. Give folks a couple minutes here to enter any questions they may have. But I know I learned a lot. I only dabbled some in the soil realm. So this was really great. And I really appreciate you being flexible and giving us your time and your expertise today.
Yeah, I'm a little passionate about soil health, so I can kind of get into the weeds on it sometimes, but I get pretty excited about it.
Awesome. So it looks like this is your service area on the left side here.
Yeah, so that's the area I cover. I mean, it's pretty flexible. You know, on the ag engineering team, we kind of go wherever we're needed, but that's my official area that I cover, and I'm based out of the Dubuque County office.
Excellent. Good to know. It looks like we had one question. How do you till the soil? Or if you don't till the soil, how do you break it up? If you don't till, how do you break up the soil? There we go.
Yeah, great question. So if you're going to a no-till system, basically the way you want to prevent that compaction from becoming a problem is, again, keeping a living root in the soil. That's pretty important, because that's what's going to build those aggregates. And people who have done this, you know, 3 to 5 years in, they start seeing much better trafficability. You know, that soil actually, when you go to a no-till system, it actually becomes a little bit more dense, but you maintain that pore structure so it can hold your equipment up and it can infiltrate water at the same time. So you do have to have the right equipment for that. You might have to make some modifications to, you know, your planter to get, you know, a little bit more down pressure in some cases to get your seed deep enough. But yeah, there's lots of ways to go no-till with very minimal soil disturbance. Even with manure injection, if you've got livestock manure, they're making a lot of low disturbance injectors now that don't move a lot of soil. So basically, low disturbance equipment, proper equipment set up for that no-till system. And then it's pretty much inevitable, if you're going to go no-till, you're going to be relying on herbicides for your weed control, because, you know, historically that's one of the big reasons why farmers tilled their soil is for weed control. Well, once you go to no-till, you don't have that option anymore. So you are going to need to be on your game with the herbicide management to make that a viable system.
Thank you for that. And on a similar note about tillage, we have a question. How does organic farmers relate to this? Or how does this relate to organic farming, as they tend to do more tillage?
Yeah, excellent question. And again, that's the trade-off. And there's a ton of scientific debate about this. If you're going to reduce tillage, you're probably going to be relying more on pesticides. Which one's worse? I don't have a great answer for that. I mean, ideally we want to minimize both, but obviously if you're organic, you don't have the option of using any of those, traditional pesticides. There's a few organic herbicides you can use, but generally you're very limited there. So you're going to be relying more on tillage. So if you're organic, there are people that are working on, growing some very large cover crops and then rolling those down with a tool called a roller crimper. Basically think about it as a really thick mulch, and you can use that for weed control. That works pretty well in soybeans. Doesn't work so well in corn. It can work in some vegetable crops and things like that. So you may be able to do some, minimal to no till for short periods of time, but if you're fully organic, you're probably going to have to do some tillage. And probably the best way to minimize the impacts of tillage in an organic system is make sure that when you're doing that tillage, you're tilling in a green growing crop, ideally. So you want to have a cover crop in the fall, and when you do your spring tillage, that's a green manure essentially is what they would call it. You're tilling in that green living plant. And when you do that, it seems to cause a little bit less disruption to the soil, less, breaking up of those soil aggregates, because you're incorporating that vegetation while you're doing that tillage. So that's another strategy, rather than just tilling up a bare soil that's already struggling because it doesn't have a plant on it and your aggregates are already starting to break down. You're going to have more erosion if you do that. So try to minimize tillage, try to incorporate green manures as much as possible.
Awesome. Thank you. Got another question here. Can you discuss surface water and housing developments and very little topsoil, because how they all relate together?
So is that surface water and housing developments?
Very little topsoil. Yep.
Yeah. So that's, on the urban side, that's definitely a challenge when housing developments go in. They're not necessarily thinking about what your lawn is going to function like when they're done building. So there's a lot of compaction there. You may not have much, depending on the building site, they may have stripped the topsoil and put it back on. You don't really know what you're working with there. So there are things you can do in your lawn to try to increase your infiltration rate. It's the same basic principles that we talk about for, row crop agriculture. You can try to do more diverse plant rotations, put in rain gardens, things like that. But yeah, minus that, you're definitely, if you've got a very hard compacted lawn, that's one problem. And then a bigger problem in urban environments is just the amount of concrete we have, because that water is going to go straight into the river. There's no chance for that to infiltrate. So definitely a connection there with water quality, probably more so due to all the concrete, but there's things we can do to better manage our urban yards as well.
Certainly. Well, that's all the questions I'm seeing, unless any pop up here in the next few moments. You pretty much hit our time right on the nail. So good job there. Thank you again for all this information. If anybody did have any questions, Brian's contact information is on the screen and it's on our website under the forum post. So you can find that. And again, this is recorded and will be shared on our YouTube page for future reference. So thank you again, Brian.
Yeah, thanks for having me. I really appreciate the chance to be here.
And talk about soils, right?
Yep.
Awesome. Well, thank you, everyone. And I hope you have a great rest of your day.
Thank you.